Okay, today is February 8th,
Yep.
2023, and we're going to, Mikhail Khovanov is going to talk about universal constructions and their applications.
Yeah, something like that.
Right. Anyways, take it away. New York City Category Theory Seminar. Go.
Thank you. Thank you. So please stop me and ask questions. So I'll talk about universal construction. Topological fields.
Those three lights. See if you can get them.
So let me explain what these are, but let us first mention. Let me mention the.
No.
Whoops.
Oh. Thank you. That's it.
Oh, better, yeah.
Okay. Sorry. Good.
So we'll at some point we'll discuss monoid categories. But for now, let us look at a special case of that. The category, what we call it N, the category of n-dimensional cobordisms between n-1 manifolds. So in this category, objects n are oriented manifolds of dimension n-1, and morphisms are cobordisms. The cobordism n has dimension n. So here we can have an n-1 manifold n null, another n-1 manifold n1, and the boundary of n is n1 union minus n null, keeping track of orientations. And this is a standard category that people study a lot in geometry and topology. You can think that this picture sort of corresponds to the case when n is equal to 2. So these morphisms are surfaces and objects are one manifolds. And so in this category, the composition of morphisms is given by concatenation. You just attach them next to each other, concatenation. And you also have tensor product. You can put cobordisms next to each other. So if we were to draw it abstractly as boxes, you have a box for one cobordism, a box for another cobordism. You put them next to each other, and that's our tensor product. So this category called N. So it's a symmetric monoid category. It's also rigid in the sense that for every object, there is the dual object. You can just kind of flip this object to the other side. So you have n minus n, and you have a cobordism from n union minus n to nothing and back, which is just identity of n, but turned around, bent back, so as to be a cobordism from either n minus n to nothing, or vice versa, cobordism from nothing to n union minus n, subject to some set relations that I can draw in just one dimension less, saying that if you compose these tubes, the composition is equal to the identity morphism. These are rigidity relations, which I always found strange because it feels like flexibility. You're able to bend morphisms, you're able to bend objects, but people who invented this, they came from algebra, so they decided to call it rigidity. I would call it flexible categories. But anyway, you know what you have, this is symmetric monoidal rigid. Usually people put rigid in front, but also symmetric monoidal rigid category. You have this dual objects, and you can.
Can I just say it has enough names? They're called autonomous, and they're called monoidal categories with dualities, and
yeah, there are various modifications. There are also various modifications.
Right. So
yes.
don't add. Anyways, but you're
not say flexible.
No, I mean it's just there are so many different names for it. Anyways, go. Sorry.
Yeah, great. So in.
But you're right about it. You know, it should be called flexible.
Okay. This is important. So usually we want to convert topological information into algebraic using various invariants, and well-developed and deep theory of invariants comes from so-called TQFTs, this is topological quantum field theory. And what it is, it's a tensor functor or monoidal functor f from the category cobordisms n into some algebraic category like the category of vector space or the category of modules. So I'll just write functor into k vect, where k is the field, and k vector is the category of vector spaces over k, usually finite dimensional. And this function must be monoidal. So the functor takes n to a vector space, it takes m to a linear map between vector spaces, and it must be monoidal in the sense of f of the disjoint union n and null union n1 must be the tensor product of f and null tensor f of n1. So this additional condition is very strong. Very strong. Sometimes there's condition for the what happens when the manifold is reversed orientation, but let me skip this. We won't need this. And so examples are in dimension n equal to 1. This corresponds to choosing a vector space in n equal to 1. Zero manifolds with orientation were just points with a sign plus or minus assigned to them. These are oriented zero manifolds, such points. So then all you need is the cobordism like this, identity cobordism from plus to plus. You need a cobordism which is this cap and a cup cobordism from plus minus to nothing and from nothing to plus minus. And you can check that all you need to have is to have a finite dimensional vector space, V assigned to a point plus, then to, for instance, vertical line, going up you assign the identity map from V to V. To a cup, you assign a map from V tensor V dual. So you can check that assigning V to plus forces your tries to assign something isomorphic to V dual vector space to the minus. And this is the usual inclusion from K to V tensor V dual, taking 1 to the sum basis vector Vi tensor dual basis Vi. And likewise, this map is the variation from V tensor V star into K. We take V and W star and send it to the variation W star of V. And I mean, anything you can do is isomorphic to this. And then the value of the circle is the dimension of the vector space.
Okay, so the fact that the functor automatically preserves rigidity is a given, or?
So I think so. This is automatic because since the category of cobordisms is rigid, this carries over to the target in the sense that on the target objects you have this rigidity built in because you can bend, because you have this setup in the original category. When you apply the functor is tensor on the objects on the image, you'll have the same relation. So it might, for instance, be, in this case, it's not the case, but it might be that the target category is not rigid, but the image will single out the rigid subcategory.
Okay.
And then I won't go into detail, but I'll just say that in n equal to 2, if you go one dimension up, you need more structure. A circle will go to B, which turns out to be a commutative, must be a commutative Frobenius algebra. So it needs to have multiplication induced by the Pence cobordism. This multiplication goes from the 2 circles to 1, so it should be a map. If B is assigned to a circle, you'll have a map from B squared to B. You'll also have a map from the ground field to B, which corresponds to the inclusion of a unit element. And then you'll have a map from D to the ground field K, and this is going to be your trace map. So you'll have a commutative Frobenius algebra B, so it comes with multiplication induced by this map, unit element 1, the image of 1 here under this cup map, and trace map. And when you write down the axle, you see that it's a commutative Frobenius algebra. And one example would be take a manifold X in dimension to n, which is closed orientable, and take even homology, even degree homology of X. And that's an example of Frobenius algebra, of a commutative Frobenius algebra. Okay, so now let us, and then it gets very complicated beyond dimension 2, you get something so-called Wittgenstein-Turaev theory, and then that gets really complicated in dimensions 3 and 5. But let us actually do something else. Let us weaken the axioms, and let us build a collection of theories that are interesting even in very low dimensions, that are very interesting even in dimensions n2 and 1, and will additionally introduce defects in our cobordisms, which will give us more structure. So let us do that. So suppose we don't have this vector spaces, we don't have this functor. Suppose we only have a variation. Well, in this picture, if you have a closed object like this, if you have a closed manifold like this, this closed manifold, let me draw it here. Have a closed manifold. It gives you a number because it's a map from identity to identity. In that example, identity is given by the ground field k. So you have a linear map from k to k, which is multiplication by some element of k. So to a closed manifold, in this theory, you're assigning some number. So let us assume that we only have these numbers and nothing else. So assume that if you have a closed manifold, closed n-dimensional manifold, then you assign it a number, and I call it number alpha of m. In case of k could be a field, it could be a commutative ring, and later we'll even look at semi-rings for connection to computer science. Is in k, and we require that it's multiplicative under the joint union, so alpha of m1 union m2 is the product, alpha of m1, alpha of m2. We also want alpha of the empty n-manifold to be 1. Well, this condition almost follows from 1, because if you put empty manifold here as one of the manifolds, then m1 union empty manifold is m1. So you have alpha m1 equal to alpha m1 times alpha empty manifold. So if this is non-zero, then this is equal to 1. But this is just to avoid the degenerate case when all the alphas are 0. This is to avoid the degenerate case. And second condition is that if m is diffeomorphic to m prime, then we want alpha to be the same, which is of course natural. And this condition comes from, if you have two of them, if you sort of have two components, if you have a manifold with two components floating like this, you'll have a number for the first component, and then a number for the second component, and you compose the map, so that's multiplying the numbers. So that's the motivation for property 1, multiplying the numbers. So you assume this is given. Such a function, and nothing else. And now from this function we want to build vector spaces, but with a weaker property than this. So we want to build a vector space in some minimalist way. So let's think about it. So we have the numbers, we want to say that to a cross-section of this manifold, and that would be a manifold in dimension 1 less. We want to assign a vector space in a compatible way, so that whenever you have a manifold n in dimension n-1, and you have a manifold m, such that the boundary of m is n. So we want to have some vector space, let me call it a of n. And we want to have a vector that I'll call bracket of m in this vector space. But at first all we have are these numbers. So to build such a system of vector spaces, one for every n, let's do the following. Let us first, so for each n, dimension of n is n-1. Let us first look at a very large vector space, which I'm going to call 3 of n. And in this vector space consists of, it has a basis of objects which are the following. So choose a manifold M. such that the boundary of M is n, as here. And let us look at possible n, so bracket of M will be a basis element in this free vector space corresponding to n. So elements of this vector space are linear combinations, sum of m sub I. Each m sub I has boundary n with some coefficients, lambda I. Finite linear combinations, formal linear combinations.
Stop for a second. Given any quantum field theory,
Yes.
you'll get this alpha, right?
You'll get this alpha, yes.
Right. And now you're saying you don't want it to come from this. You want it.
Yes, just want an alpha with its properties.
Okay. So alpha goes from closed manifolds to vectors.
Yes, closed manifolds to numbers.
To fields.
To numbers.
To numbers.
Yeah.
Okay. And this is some type of extended topological quantum field theory. I mean, that's what they do there. They chop up.
So we'll see. So let us see the properties. Let us look at the properties of this construction. So let us first build a vector space for every n-1 manifold.
Right.
So
Okay.
how do we do this? So first, let us build a very large vector space where we look at all manifolds M that bound n. And so each of them is a vector in our vector space. And we can form any linear combinations of these vectors. So this is very large vector space. Now let us define a bilinear form. The bilinear form is going to go from free of n times itself, free of n, into the ground field. So the bilinear form is the following one. So take two such manifold M1 and 2, whose boundary is n. I'll just draw it schematically, M as M1 and M2.
And do you want diffeomorphism classes or just?
It's not going to matter. I mean, it's not going to matter, but you can do either. So let us reflect one of them. So let us reflect M1 and do it to the top of M2. So this is M2. I call this M1 bar. So we reflect M1 and do it to M2 along M. So we get a closed n-manifold, which we can now evaluate using alpha. So define this to be alpha of M1 bar M2. And now we extend by linearity. So that on linear combinations, the bilinear form is given by the corresponding sum. So we get this map. We can put here as a product over K. So now let us define the state space.
So 1 second. So you have this vector space, this formal vector space, and now you're making it into some type of algebra, or it has an
So now
evaluation.
it's just a bilinear form. So
A
now we
bilinear
just
form.
define a bilinear form in it.
Okay, and something is it well defined? If you chop it some other way,
Well, if you chop it some other way, you might get a different manifold here. If you
Right.
chop it here, maybe it's a different manifold. Maybe it's the same manifold, but we'll discuss materiality in a few minutes.
okay.
In a few minutes, we'll discuss materiality property of this. So let us define the state space. So state space of manifold n state space, vector space, as the quotient of free vector space generated by n modulo the kernel of the bilinear form. So what does it mean? Oh, so here we still have the symbols of every manifold m with boundary n giving us a vector. It's a vector in here. But now there might be relations. So we have a relation that some lambda I bracket mi is equal to 0 in A of n if for any m whose boundary is n. If we can do m to we can reflect m and do it to each mi to get a closed manifold. We evaluate it using alpha. And now we take, so this is a number in our field K, times Li, and we want the sum over I to be equal to 0. So that's the condition for linear combination of this manifolds with boundary M to be 0 in the quotient space. For any M, this must be equal to 0. Now that's a very strong condition because this must hold for any M. So that's lots of equations. So if you were to randomly choose your evaluation alpha, so chances are there's going to be no relations. And everything is going to be linearly independent. You have a very large state space. And we want to avoid this case. So we want the spaces to be small, for instance. We want the state spaces to be finite dimensional over field. But nonetheless, so this is the definition. Why is it a natural definition? So we claim that this has functoriality properties. So given a cobordism, it induces a map of the state spaces. So let us check that. So suppose you have a cobordism M from n-1 manifold n0 to n-1 manifold n1. So then we first claim that M induces a map of large vector spaces, 3 vector spaces on n0 and n1 as follows. So we can take a manifold m0 with boundary n0. So then, let me shift this a little bit. So like this 3 and 0 here, 3 and 1 here. So given a manifold M0 with boundary null, we have it simple, a basis vector in 3 of n0. I mean, what we can do, we can take n0 and compose with M, glue the boundaries together. We get a manifold M0 with a boundary n1. So let us set up a map, a linear map here denoted bracket of M, which takes a symbol of M0 to the symbol of M and 0. So it's a map from basis vectors to basis vectors. And extend by linearity.
Okay, since we're talking about notation, or not notation, but names, can you justify calling that a state space?
It's so we're going to deal something like a topological theory, or a topological theory. So in this situation, to an L-1 manifold, we assign it state space, or it's the value of the functor on that object. You can just call the vector space assigned to, terminology is up to you.
No, I understand.
But let us sort of continue so we get this map. But we claim it as induced map on the quotient spaces, on the state space from A and 0 to the state space of A and 1. We claim that the same map, taking a symbol of M0 to the symbol of M and 0, the composition is a well-defined map. And this requires checking that it respects kernel. So if something is in the kernel, something here is in the kernel of the bilinear form, we need to check that after this application of M is going to be in the kernel of the bilinear form. So suppose you have an element here in the kernel. So we have some M sub I, symbol M sub I, lambda I in the kernel of the bilinear form for n0. In the kernel of bilinear form for n0. So it's 0, so it's 0 here. Now, so that means that no matter what you attach to it, take the sum, you get 0. Right? Attach, abbreviate using alpha, you get 0. Now, if you apply M to the sum, you're going to get some lambda I, mi, in here, in the free space 4 and 1, right? Why is it in the kernel of the bilinear form for A and 1? Well, we need to check that no matter what we attach and evaluate, we get 0. So let's check that we attach something, m tilde, or so-called m prime. So we attach it and evaluate, we get some lambda I alpha of m prime bar and mi. But so this was in the kernel for a null. So if you take this piece and attach it to each mi, then of course we have 0 in the sum. So we're saying that the map, this map takes elements in the kernel to elements in the kernel. So it descends to a homomorphism from a linear map from the state space for a null to the state space for N1. So it's a well-defined map. Great. And also composition goes to composition. So if you have one cobordism M from N0 to N1, then you have another cobordism M prime from N1 to N2, then you have state spaces A and null, A and 1 and A and 2, and we have induced map, bracket of M, bracket of M prime, and bracket of M prime M. And this is a commutative diagram, so composition, concatenation of cobordisms corresponds to composition of maps. So this map is equal to M prime M. So we get a functor. So we get a functor. Let me call it A or A sub alpha. Functor from cobordisms for n-manifolds to vector spaces over K. So to n-1 manifold n, we assign the state space A of n, and to a cobordism M. Between n-1 manifolds, we assign the linear map bracket of M.
Oh, so somehow this A is somehow the most. It has all the information in it. Well, that agrees with alpha.
Yeah. So this is so we get a state space, but again, so what happens? We have evaluations of closed n-manifolds, right? We have these numbers.
Right.
Now we look at cross sections. So for every whatever you can have in a cross section, something n, we look at everything that bounds n, and use this to generate a state space. But we mod out by the kernel of the bilinear form.
Okay, so now I see what you're doing.
So additional property of this construction. So it's not a TQFT, but we have a weaker property. So if you take a state space for n and a state space for n prime, this is a subspace of the state space for n union n prime. So let me explain this point. So elements here are linear combinations of manifolds M whose boundary is n. So manifold M whose boundary is n. They generate the space. And this space is generated, I'll draw M prime, and some manifold M prime whose boundary is n prime. So the space is generated by vectors of this form. Now, you can just take the disjoint union of this. So this is bracket M, bracket of M prime. And you can just map it here as the disjoint union. So send bracket of M times the bracket of M prime into here as bracket of M union M prime.
So why is that weaker than the regular TQFT?
Yeah,
because
yes. So,
oh, sorry.
well, you can check that if you evaluate against something for n, something for n prime, everything matches. it's a product. But what happens, you might not capture the whole space, because in the state space for n union and prime, you might have some manifolds m, double prime, that do not decompose as the linear combinations of manifolds of this form, something which bounds n, union something which bounds n prime. So this might not, so in the state space, a n union prime, so bracket of n prime, n double prime might not be equal to any sum lambda I, bracket of mi, union bracket mi prime. So in other words, so the image might not be the whole space. So the image respects bilinear form, but it might not be the whole space. We'll look at some examples.
Yeah, I have a question. I'm still confused about going back to the previous example. Before we were talking about multiplication of objects into another one, right? And in the top, yeah, not there, the diagram right to the right of that. Yeah. That one, yeah. But going from n1 to n2, right? This is a kind of factorization, right?
Yeah, so let me maybe just let me just make it a little bit more complicated. Say that this is maybe n2, this is m prime. Just because I draw a very simple diagram with very few circles, etc. But just to emphasize that.
Oh yeah, but I just mean like you know, I understand how you go, you know, multiplication, you turn two objects into that one object, and that's the manifold. But the reverse direction, turning one object into two objects.
Yeah, you can do anything. So there are all kinds of cobordisms. You can have a cobordism between any number of circles to any number of circles, and anything can happen in between. The cobordism can have many components. So for instance, you can have a cobordism, something like this. Also
okay, well, I guess it makes sense. It's just the inverse of the multiplication, right?
Yeah,
so
yeah. So of course
string
you can,
theory.
many things you can do, but if you look at this cobordism, you can indeed explain that it's dual to multiplication under some rotation.
Okay.
And you can make sense out of this in the language of rigid categories, like those U-turns. If you add U-turns everywhere to this cobordism, you can go back to the opposite cobordism where two circles merge into one, and that's part of the story about rigid categories, and that's related in dimension 2 to the property of Frobenius algebras because of this trace map epsilon from the algebra to the ground field, but it's not degenerate in some sense. Because of this map, you can convert multiplication into co-multiplication by dualizing it.
Okay.
So it's part of the rigidity structure of the sphere. Okay. So coming back to this, so we're saying that in a TQFT you have an isomorphism in a TQFT. But here we have something weaker, we have inclusion over a field. We don't get TQFTs in general, but we get lots of interesting examples. So let me give you some examples.
Is there any time when you give a certain alpha where it would be an isomorphism?
Yeah, but then we have a
trivial.
Well, I mean, definitely. Let's look at one. Let's look at a simple example. If for instance, if to every manifold you assign number 1, then any alpha of any m is 1. That's not very interesting. Then for any n, you have the state space AFM, then any for any m, bracket of m is equal to bracket of any other m prime with the same boundary. And you get a one-dimensional vector space and trivial identity maps for any cobordism. So this is a very degenerate trivial example. So let us look at something more complicated. Let us work in the case of surfaces. So we're in 2 dimensions. when we are into dimensions, we can explicitly describe all closed n-manifolds. So again, we restrict to orientable manifolds. So in dimension 2, any manifold, oriented manifold, is determined by the genus. Closed oriented. So to get an evaluation function alpha, we just need to have an evaluation of each surface of genus G for all G. So we need, let us say that evaluation of the surface of genus G is some number alpha sub G in the field K.
This goes back to his question about diffeomorphism classes.
Yeah.
In other words,
so I raised it, but we particularly said that if M is diffeomorphic to M prime, then alphas are equal.
Okay,
But also to answer your question, if M and M prime are diffeomorphic real boundary, if they're diffeomorphic, then necessarily they are equal, no matter which definition you use, they're going to be equal in the quotient space, in the state space, if they're diffeomorphic real boundary. So let's look here. So we take a surface of genus G assigned to some number alpha G, and those numbers determine the theory. So we can combine these numbers together into generating function alpha null plus alpha 1t plus alpha 2t squared, where t is a formal variable. So let me call this function G alpha of t. So it's a sum alpha sub G, t to the G, G greater than or equal to 0. This is formal power series and one variable t. So for each such power series, we have one topological theory. So
and for this nice case, it's an isomorphism. It does.
For which you almost never. So it's almost never. So for now, this is very general, right? Pick any numbers, form this generating function. Let's see what we get as the theory. So let's start with one circle. And one circle can bound a surface with some number of handles. And let us call this, call it say mi, and I'll just denote the corresponding vector in the state space by v sub I. So I is the number of handles. In this example, I is 3, but we can start with 0 handles when it's a disk, and so on. And let us look at the bilinear form on the state space of a circle. The state space of a circle. So it has this set of spanning vectors, v sub I. So let's write down the matrix of the bilinear form. So the matrix of the bilinear form. On the rows and columns are labeled by 0, 1, 2, 0, 1, 2, because we can have vectors v0, v1, v2 as our spanning set. So on the intersection of ith row and jth column, we should take surface of genus I with one puncture and the surface of genus J, one puncture, and glue them together. Then we get the surface. We get the surface on genus I plus J, which is closed. And that surface evaluates to alpha I plus J. And this is the matrix of the bilinear form. And these matrices are well known in mathematics. They're called Canfield matrices. So they have the property that on each antidiagonal, the numbers are equal. So alpha null, alpha 1, alpha 2, alpha 2, alpha 2, etc. Alpha k, alpha k, alpha k.
Because there's lots of different ways of decomposing the diagonal. In other words, if you have 15 circles,
exactly. You can cut here.
Right, you cut there. Right.
So that's a Canfield matrix. And in our case, it's infinite, because it's got many rows and columns. And for generic, if you randomly choose alphas, this matrix will have infinite range. In fact, which is random axle below relations on rows and columns. So there's a theory which goes back to the 19th century for when does this matrix have finite rank. Because we want to have finite dimensional theory for every manifold n. So we want this matrix to have finite rank. So the theorem is essentially homogeneous. So let me state it. The Cantor matrix X, H with n is alpha I plus j, and the ij for a column has finite rank. If and only if the generating function g alpha t has the form some polynomial in t divided by some polynomial in t. So how do you prove the theorem? The theorem, well, you check that. So if you want to have finite ranks, at some point one of the columns must be a linear combination of previous columns, and that gives you a relation for every row. And so when you look at these relations, you see that you have to have the following. So you have to have alpha, say, n plus k should be equal to b1 alpha n plus k minus 1 plus b2 alpha n plus k minus 2, etc. plus b sub k alpha n for some k and b1 bk and all large n. For n starting from some position, you have to have this recurrent relation. So next number must be a linear combination of k previous numbers with fixed coefficients.
Right. Just to remind you, you said it before, but why is finite rank important again?
Yeah, because so we want to get interesting examples. So for interesting examples, we need to have non-trivial relations on the combinations of manifolds with a given boundary. Mm-hmm. So we want the kernel to be non-trivial. Even better if you get something small. So the best case scenario, in some sense, if the state spaces are finite dimensional. But here, in fact, if you don't have this, the kernel is trivial. You have to have either this or trivial kernel. In this example, there's nothing in between. So this means that the sequence is recurrent. Recurrent sequence. So it's the next number is a combination of previous numbers starting from some position n, for all numbers starting from some position n. And we can check that this is equivalent to the generating function being a ratio of polynomials.
So if your alpha sub g's are good, then this is going to be a nice, not a topological quantum field theory. You don't have a name for it.
This is very rare. Isomorphisms are very rare.
Yeah, so broken topological quantum field theory?
I call them topological theory. I just call them topological theory, but I mean, I don't think there's any established notation.
So even if that has finite rank, it still won't be a TQFT?
It's very rare. So I keep forgetting the condition for a TQFT, but the generating function, it must decompose into sum of functions where every denominator is linear, so something like 1 minus lambda IT. And I keep forgetting if I should put a fixed number or not here, so I forgot whether m is actually maybe equal to lambda i's or not, but and plus maybe very small, plus maybe a constant term or a linear term. So very few examples of TQFTs. Well, let's look at one example that's not a TQFT.
Stop for a second. The purpose of a TQFT is to give invariance to open manifolds. It's easy to give invariance to...
to manifolds with boundary. You get the vector in the state space.
And now you have something else, topological theories, where they're not giving invariance to
you get them for every time you have a manifold with boundary, it gives you a vector in the state space of the boundary. So you still have vectors assigned to manifolds with boundary. It's just that the state space is more complicated. It might not be the product of state spaces for individual components, but something bigger.
Okay. A physicist who gets the emails asked me today, he says he looked up TQFT and he said, it has nothing to do with physics. And I said, right. And now I want to just make sure it has to do with geometry.
So let's do an example where the function is very simple, so it's just a constant. So there's nothing beyond this. It's beta plus 0 t plus 0 t squared plus etc. And beta is a non-zero element of the ground field. So let us look at the, also say that once you know that this function is rational, then the state space for a single circle is finite dimensional, and you can check that the state space for any number of circles is finite dimensional. That's easy, because this relation tells you that if you have the surface of genus n plus k with boundary, you can reduce it to linear combinations of surfaces with lower genus. So you have an upper bound on the genus. And then you have an upper bound on the genus of every component, so the bound of components can be limited, and then for a given number of circles, there are only finitely many possible configurations of manifolds with boundary. You need to partition, you need to take your circles and partition the boundary into disjoint unions, which would bound different connected components of the manifold. And then each of them can have some genus, but not very high genus, because anything higher you can reduce. So it's easy to see that this implies that the state space of any number of circles is finite. There are only finitely many configurations of how to distribute circles among connected components. Okay, so let us look at an example of when the generating function is constant. And this means that anything of genus 1 and higher evaluates to 0. Yeah, let me point out that this is joint work with Yakov Kanonov and Viktor Ostrik. So let us look at this case. Then this tells us that this vector is 0 in the state space of a circle. So why is it 0? Because no matter what you couple it to and evaluate, you get 0. So if you couple it to, it has genus at least 1, possibly higher, so it evaluates to 0 for this function.
And your matrix is definitely finite rank.
Yeah, let's write down the matrix. The matrix is 1, 0, 0, 0, 0, 0.
Everywhere
The
else.
matrix has rank 1. So of course for genus 1, this is the next column, so it's 0, so this vector is 0.
I would have thought it's a B instead of the 1, but yeah.
Oh, sorry, you're right. Great. Yeah, thank you. So this is 0, so that means we can reduce the surfaces of genus 0, but possibly with some number of boundary points.
That's extremely uninteresting. I mean, this.
Yeah, I'm sorry.
No. This example, that's not. That's highly degenerate.
It's a degenerate example.
Right.
Okay, so what happens here? Well, let us just look at the state space of a single circle. So state space of A1 of S1. Well, it has this vector, and then you couple it to itself, you have beta. So the matrix of the bilinear form on this basis vector is just beta. So this vector space is one-dimensional with basis. With basis this just one vector basis. Let us move on to two circles. So what can happen to two circles? Well, we only look at genus 0 manifolds with bound to circles. There are only two possibilities. This one and this one. So let us write down the matrix of this bilinear form. So we shall take, let's say, this, the row pictures reflect and glue to the column pictures and evaluate. So if you do this reflect and glue, you get two spheres. That evaluates to beta squared, because each one is beta. If you take this, reflect and glue here, you get a two-sphere. So that's beta. Well, the matrix is symmetric, it's beta, and this is 0, because if you glue them together, you get a torus, and that evaluates to 0. So this is 0. So this is the matrix of the bilinear form. You take as determinant, we get minus beta squared. That's non-zero, so that means that the matrix is non-degenerate, so this is a basis. So this is a basis for the state space of two circles, S1 union S1. Okay, so if you continue, if you look at the state space of three circles, I'll just write S1 union 3 times. Well, you can, in this case, there are 5 possible vectors you can draw. You can draw this vector. You can draw 3 vectors of the form where you connect two circles by a tube and the other one by itself. There are 3 such vectors. And there's also so this vector, so there are 5 vectors. You can write a 5 by 5 matrix that's symmetric. You can compute that the determinant is not 0, so that's a basis of the state space for 3 circles, 5-dimensional. Now, if you go to 4 circles, you can still play with this vector, but you find one relation, which I'll write down. Notice, of course, that the symmetric group acts on the state space by permutations. You can permute, and that doesn't change the space of relations is invariant under the action of the symmetric group. So it turns out that on 4 circles there is a relation. But I'm just giving you to make the argument that even this degenerate case is not completely trivial.
No, so it is interesting.
A little bit, so maybe so in this case you can.
How many elements in the basis for 4?
So you can count 15 pictures like this. There's one relation of them.
So Catalan numbers? Is this?
It's actually get Catalan, so yeah, you get 15 minus 1, 14, so you'll get Catalan numbers. So the relation you'll see is that, so first of all you can have, I'll just write sum of 3 terms here. You can have a picture like this where you can connect the first circle to one of the 3 remaining circles, as we turn, and connect the other two circles together. So you get a pair of such arcs. So there are 3 terms, I'm going to group them together. There are 3 terms, then minus sum of 4 terms where you pick one and cap it off and connect the other 3 as one component. That's the sum of 4 terms, like this. And you have plus beta. This equals 0. So you can check if this relation holds directly by pairing with anything else on the other side and checking that you get 0. So what's the meaning of this? If you look at all the related pictures, so when one picture stands out, So in this picture, where you pair 1, 3, and 2, and 4, one of these three pictures, it has this intersection in it. So this relation says that this intersection can be reduced to the sum of terms without intersections, where pictures don't have intersections. So this one doesn't have intersections, the other two do not have intersections. It's this one and this one.
All three of those are diffeomorphic, right?
Well, they're related by permutations of the boundary circles. You connect by the symmetric group and then taking one to the other. So you can add by have a symmetric group action on them. So and the relation is invariant on the direction of the symmetric group if you apply any permutation of the symmetric group, if you use a cobordism. If you apply any permutation of the symmetric group, the relation is preserved. But, so we can single out this picture from everything else, because everything else has a presentation without crossings, has a surface without crossings. And so you can, so it tells you that if you have this intersection, then it can be reduced. And then after this, you can indeed reduce the crossingless matchings and Catalan number. So maybe skipping some details, let's just take the theorem on this joint paper, that if characteristic of the field K is 0, then dimension of the state space of K circles is the K Catalan number 1 over K plus 1 to K choose K Catalan number, which is the number of crossingless matchings where you choose 2 K points on a horizontal line, and you look at all ways to match them by K disjoint arcs in the lower half plane.
This is coherence there. It's Stashev's pentagon.
Yeah, well, if you're able to reduce these crossings, and then we can check that this is the only relation, at least in this case.
What about when you have 4 circles and 2 of them are connected and 2 of them are just cups?
So if you have 4 circles, so there are some other, there are 7 more, so this is 8 possibilities for genus 0 conversions that bound for circles, and there are I think there are 7 other diagrams, like this diagram or this diagram.
Right.
And they don't enter the relation. There's kind of sort of, in this example, in this particular example, there is separation. There are 7 diagrams that don't enter this relation, and they don't have any relations on them. And there are 8 diagrams which have a relation which is S4 invariant under the symmetric group action. But again, it's for this particular function. So for other functions, there are other relations, other state spaces.
Is this characteristic condition necessary?
I think yes. I think so. I think in finite characteristic you'll have more relations, so you'll have smaller state spaces. Okay. So this way you get categories. You get topological theories. You can think of them as categories because you have for every number of endpoints, you can look at the cobordisms and the linear combinations, and so you get the category this way. So you get some interesting categories. And so this is sort of just one. This is one example of a universal construction. It's in dimension 2. And if you get new interesting categories, and most of them do not come from TQFTs. So let me just give you a hint of like an idea for next lecture. So this is the next lecture by Mikhail. And what we did in several papers.
Okay, so 1 second. So this is an advertisement. So let's. This is an advertisement for next week's Misan Im is going to talk about. I don't remember the title. Remember? Hold on.
Yeah, it's probably about automata and topological theories.
All right. Shoot. Hold on. Right, so next week is Misung and automata and topological theories, right?
Yeah, so,
Okay.
so in computer science and in the theory of formal languages, there's an important notion of regular languages. Regular languages and automata. So an automaton, it has some finite number of states Q. Automaton, it corresponds to there's some alphabet, finite alphabet, sigma with letters A, B, C, etc. And then automaton, you can be in some state Q. You're reading a word A1, A2, AN. This word is an element of the free monoid generated by sigma. It's the monoid of words in letters in sigma. And so as you're reading this letter, you're going from state to state. And let's say at some point you're in the middle of the word, the next letter is A. So you have several possibilities. You kind of look at your rules, and your rules say that from a given state Q, using letter A, you can jump to several more states. So you can choose where to jump. Then you go to the next letter, so on and so forth. At the end, there are many choices. At the end, you can end up in some state. So some states are accepting, you draw them by double circle. If there is a way to jump, and end up in accepting states for a given word, you say that the word is in your language. So the word omega then is in your language L. And if there is no way to start, let's say, from initial state and follow the jumps that are allowed for this word and end up in accepting state, then omega is not enough. And this way you get a language. And languages, so language L is a subset of the set of all words in the alphabet. And the language is called regular if it corresponds to some finite automaton. So the notion of a regular language, so it corresponds to some finite state automaton. And so we are able to relate this, interpret this regular languages and automata using topological theories and TQFTs. So why is it a topological theory? I mean, what's the topological theory here? So remember that we start with evaluation of closed manifolds to numbers, right? Using alpha, we assign them to numbers. So here let us do the following. Let us draw a line, put dots on it. So we think of a line as one manifold. We think of dots as some kind of defects, zero manifolds, and they come with labels A1, A2, AN. And let's say we have orientation, so our one manifold is oriented. So we think of this one manifold, this interval with label dots, as the analog of a manifold. It's one-dimensional, but to make it less boring, we decorated by defects with labels. So the defect of this one manifold is describing a word omega, A1, A2, AN. And if the word is in the language L, then we assign to this interval of omega, we assign to it 1. And if omega is not an L, then to this interval divided by omega, we assign 0. So we need this system, we need some analog of k which have 0 and 1. But turns out that the right thing here is to say 1 plus 1 is 1. So we only have 0, 1. The word is either in the language or not. So we're just going to say that we replace k was a field, we replace it by the Boolean semi-ring B with 0 and 1. But it doesn't have subtraction, it only has addition and multiplication, and 1 plus 1 is 1. It's Boolean semi-ring. And then, so floating like this interval, thinking of it as a closed one manifold with decorations, it's 1 if word A1, AN is in the language L, and it's 0 if the word is not in the language. And then you can say, well, here we cut the manifold by cross section.
So you're going to cut the words up.
So we can cut the word like this. This is a cross section.
Mm-hmm.
So we have a state space of the point. Point is oriented plus or minus. And then you can check that the state space A of the point, say plus or minus, is finite. So it's going to be a vector space, but over B. So it's a module over B. So you can add vectors. So you can check it's finite if and only if L is regular. If a language L is regular. Because what you need is a language. You need to evaluate this intervals of operation. That's fine. That's fine. So this is analog of finite dimensional state spaces. But you can say, what if I have more than one endpoint? So if you have two endpoints, for instance, you can create an arc and put dots on this arc with some labels d1, dm. And when you compose, you close this up. You can close this up into a circle. So you also need an evaluation of circles if you want to build a topological theory out of this. So you need to pick a language L to evaluate your intervals with dots. So it will correspond to words. But you also need to pick a language to evaluate circles. So you need additional language, we call it L-circ. And this language is circular. So if a word is in the language, then any rotation of the word is in the language. So omega 1, omega 2 is a null, if and only if omega 2, omega 1 is a null. So circular. So given such a pair, we can build a topological theory with state spaces. And we can check that the state spaces are finite. Finite is the analog of finite dimensional. It's finite if and only if both languages are regular.
But these defects make it like a different setup now, right? Like than what you had before.
Yes. So it's strange because we, like in dimension 1, there are almost no interesting manifolds, right? They're just interval and circle, but we forcefully introducing more decorations. We're forcefully introducing more structure, specifically adding dots and also picking a label for every dot.
But with the topological theories you had before, like now you're what I guess I don't understand.
So before, for instance, so we discussed this theory, right, for surfaces. We got interesting examples, but the evaluation has fewer parameters. We just need one number for every genus. But here you have a giant number of parameters. Well, not in both cases it's infinite, but here it has sort of exponential growth because for every sequence of letters, you need to choose 0, 1.
I see.
But of course, there are some patterns in the sense that if your language of words which are evaluated to 1, if it's not regular, then the state space is infinite. And you need the circle language. And there is also a variation of this. This is in a very recent paper joined with Misongim, and also Remy Kaldavi and Zachary Lin, who are...
Could you write it?
Yes, I'll write down the names. Misongim. So that paper is on the archive last month. Remy Kaldavi, Zachary Lin. And Paul Gustafsson. So Paul is a postdoc at UPenn. Remy and Zachary, they are undergraduate students at Columbia. So this came out of our reading research course. Misongim is a professor at USNA. And in some sense, it's even for this paper, it's a little bit even more basic. We're just saying that, so here, you take this pair of languages, language for intervals, language for circles, we do universal construction, we get over Boolean numbers, and we get this topological theory. But in this paper, we're saying that if you have a finite state automaton, Q, to the automaton, you can actually assign a TQFT, not just a topological theory, but a TQFT. And in this TQFT, the state space, of the point plus is just the all Boolean combinations of the states of the automaton. So an automaton has states Q, many states, and transition functions. So it's very simple. So to point plus, we assign the Boolean combinations of states of the automaton. That means subsets of states of the automaton. And if you have a line with a dot labeled A, so that's a cobordism from plus to plus. To that you assign Boolean map from Boolean linear map from the free module on Q to the free module on Q, which to a state Q takes it to the all states Q prime that can be reached, all states Q prime that can be reached from Q using letter A. So all the states which you can reach using, so that's Q prime using A. And then you can also do this kind of, because you have intervals, when you cut an interval in the middle, you have half interval. So when you need the sort of the meaning of this half interval. The meaning of this half interval is the sum, formal sum of states Q that the initial. So you have an initial state in automaton, but you can also allow finitely many as collection of initial states. You can say these states are initial, you can start from any one of them. It's fine. And then the value of this half interval is you take a state and see if it's accepting state. If it's accepting state, it's 1, otherwise it's 0. So you can, these pictures make sense out of initial states, accepting states, the transition functions for every letter of the automaton, and again, an interval before omega is in the language if it evaluates to 1 using this rules. And you also get the circular language this way from each automaton, but we don't know how to characterize, you don't know enough of the literature, so it's probably in the literature somewhere, but we don't know how to characterize circular languages that can be realized as traces of automata. So given a circular language, figure out if it comes from some automaton. We don't know what's the characterization. So there are some kind of various questions, some basic questions are not answered, but again, we don't know the literature. Maybe this is well known. But the amusing fact is that we can take a well-known theory of automata that's been around, automata were discovered in the mid-1940s, and we're now saying, well, this is just TQFT in disguise. And the disguise is you have to switch from a field to the Boolean semi-ring B. You have to switch to the Boolean semi-ring B. You need to be in dimension 1. You ought to have defects labeled by letters. And you ought to have this half intervals. You have to allow intervals floating inside your cobordism, not just circles. So it's sort of amusing, but I don't think it's a kind of, I don't think there's no deep theory here for now, but it's just an amusing observation that you can grow. You can go to dimension 2 and say, let's say I'm in dimension 2 now. I want to study Boolean TQFTs and theories, and I want to keep my defects but extend them. So here defects are zero-dimensional, labeled by letters of the alphabet. In dimension 2, you can have more complicated defects. I can have defects that are zero-dimensional, so there are dots that float on the surface, but I can also have defects that are circles that also can kind of move inside the two-manifold. And maybe I can have more complicated defects that are networks, etc. And you can ask what's the analog of the automata. So people have studied high-dimensional variations of automata. We don't know if they probably don't match exactly what happens on the topological side in 2 dimensions. This is worth exploration, but I think this is completely unknown. I don't think anyone has studied 2-dimensional TQFTs with defects over Boolean semi-ring, but this is one natural further development from here. So this was an extended advertisement for the next lecture, but I'm not going to do Josh's lecture.
Well, I do have a question, and I guess I'll see more. But the negative to the positive, right? That just represents a direction that you're going around the circle, either clockwise or counterclockwise.
Yes, because you need this. So it tells you that the state space for the minus point must be the dual of the state space for the language. You can of course formally, this is a free module over B, you can dualize. It's also free, but it's a free module over formally just the dual of the set. So it's just a set, you just label, you just think of the elements as being dual to elements.
And the W1, I kind of missed this part when you mentioned it, but W1, W2, basically to make a new word in the circular language, W1, W2 has to be the same as W2, W1.
Yeah, so the thing is that if you're in a circle, so if you put some sequence A, B, A, C, then no matter where you start, it should evaluate to the same. So if I start here at A, B, A, C, I get a sequence that evaluates to some number, right? Or I can start here, it's A, C, A, B. It must evaluate to the same number. So the variation must be rotationally negative.
Yeah, okay.
And that's what I mean by this.
Okay, got it.
There it is. Thank you very much. Josh, you want to
Yeah,
talk? Or you
great
want to?
stuff.
So in the third lecture.
Hold on. Okay, go on.
Thanks. So in the third lecture, it's a little orthogonal to the first two, so we're going to go back up to dimension 3. And the potential applications is not to classical computation, but maybe towards quantum computation. So that's the hope, but I'll review some things about three-dimensional TQFTs.
Thank you. Okay. Any questions? I mean, there's a lot of stuff.
Did you define, what was it, the universal construction?
Yeah, we call it universal construction. So again, we start with evaluations of kind of closed manifolds or some closed structures, closed systems. So it was manifolds at first, but this became this intervals with dots and labels, or circles with dots and labels. It's very low dimensional. It's one dimensional, but it's still amusing because we're getting automata and regular languages. But you have to change the ground ring from a field to a semi-ring B. So B has no subtraction, it's only addition, which of course makes it much more complicated to work on because you don't have linear algebra available. So it's much more awkward to work over B than over a field or a commutative ring.
So universal construction is just a framework for all of these?
Yeah, for all of this,
okay.
and you don't need the field. So you want a ring or a semi-ring, and it must be commutative because if you assign some number to this manifold and you assign some number to this manifold, there's sort of floating the n-cobordism from the empty manifold to the empty manifold, you can change their position. You can reverse the position. That means that the product of these two numbers must be equal to the product of them in the opposite order, so your ring must be commutative. But as we see here, it doesn't have to be a ring, it can be a semi-ring, but also commutative. So like for instance, try tropical semi-ring. There's nothing, I don't think that anyone had looked at this. People have looked at tropical automata, but not tropical TQFTs or tropical topological theories.
There is some type of adjoint functors with finite automatons. Something.
Yeah, I'm aware of kind of there's very large amount of literature.
It's in McLean's book. Something action versus something else. I don't remember.
Yeah, it would be interesting to try to involve other category theory that's already known for automata. See if you can merge it with the kind of category theory and one of the categories we see here in the universal construction story. But I do also want to say that you can do universal construction in any monoidal category. So you have one monoidal category, you can tensor objects, you can tensor morphisms. So you should start with evaluation of morphisms from identity object to the identity object, because these pictures, when you have no boundary, go from the identity object to the identity object. So if you're in the monoidal category, you can tensor.
From the unit to the unit.
So you can have diagrams like this would be, this is maybe a map from X tensor Y to Z, but you can create a complicated network of these maps. And as long as the network is from nothing to nothing, it gives you a morphism from identity to identity. So in the universal construction approach to monoidal categories, you will start with an evaluation of these closed networks, and then build state spaces using the same story. So you get some kind of modification of your category with new relations. So you can do universal construction in any monoidal category, and there's also some variation for non-monoidal categories. When you're just in a category, maybe you know where you start, you know where you finish, and you can evaluate any say morphism from start to finish, and then you can cut in the middle to build state spaces. So there are also variations like that.
How is this related to extended topological quantum field theory?
So
goes higher dimensions.
Extended theories are more subtle. They're more subtle. I mean, at some point, if you play with extended theories, at some point you realize that beyond dimension 3, in dimension 4 most of the time, at some point you need to pass to homotopy categories. The category of complexes modulo homotopies, and this kind of raises the complexity up, and that's a big complication. And here, you can explore something similar here. For instance, you can explore some n-log of a DG structure, differential graded structure here. And for instance, you can look at recent paper of Josh and his collaborators, where they built a large number of derivations on a certain universal construction, on a certain monomial category built by universal construction. So they have lots of derivations with a sort of even n-logs of DG structures that you can have on categories to make them triangulated, and also to do TQFTs in dimension 4. Because most of the time you need DG structures there. So it gets complicated, but we hope that this story will grow further. And I also can talk about forms. I don't know if you'll have time to cover forms or not.
Probably not.
Which was another motivation for your construction, but let me stop here.
Okay. Anyways, thank you very much. You get one free donut, a cupcake my daughter Rivka made, and everyone could take one free donut. Those are stupid donuts in there. Anyways.